Welcome to The Explainer. Today, we're unpacking a genuinely groundbreaking paper by Alejandro Rodriguez Dominguez titled Dynamic Causal Portfolio Choice, Hedging the Rotation of the Common-Driver Manifold. Look, if you're into quantitative finance, portfolio theory, or complex dynamic systems, you are absolutely in for a treat today. This paper completely reimagines how we manage risk over time. It literally takes us miles beyond the standard models we're all used to. So, grab a coffee and let's dive right into this.
Right off the bat, this is the central question we're tackling. Just imagine for a second that you're holding a perfectly optimized portfolio. You know the drill. You've crunched the numbers, you've carefully balanced the weights, and you're ready to let it run. But what happens when the underlying rules of the market itself, like the invisible geometry that governs how your assets actually move together, what happens when that fundamentally changes while you're holding those assets? Seriously. Can you hedge against a risk that doesn't just move your assets around, but actually shifts the very landscape they're sitting on?
Here's a quick roadmap for our journey today. First, we'll look at the static snapshot problem, then hedging the moving landscape. Third, we'll break down flow, swap, and refinement. Fourth, we're covering the unhedgeable jump. And finally, tracking the time-dependent frontier.
All right, let's kick things off with Part 1, the static snapshot problem.
To really grasp what this paper is doing, we first need to lock down its core concept, the Common-Driver Manifold. Think of the market as this hidden, constantly shifting landscape. The drivers here, they're basically the tectonic plates underneath everything. Conditional on these specific drivers, all the cross-sectional co-movement between your assets is totally explained. Basically, the assets become independent of each other because all their shared risk is completely 100% captured by this manifold. It's the geometric structure that dictates the whole shebang.
Now here is the fatal flaw with traditional Markowitz or static mean variance models. They treat that landscape as if it's set in stone. They take a single isolated snapshot of the common driver manifold, and they optimize based on that one frozen picture. But the author makes a brilliant point here. He argues that the conditioning representation, this manifold, is actually the natural state of the problem, and it moves. Sensitivities change, the actual set of drivers changes, the geometry rotates, and sometimes it violently jumps. Using a static snapshot model is honestly like using a paper map from 1995 to navigate a modern, bustling city. A dynamic causal model, on the other hand, is like having a live GPS that's tracking the shifting terrain in real time.
Which brings us nicely to Section 2, Hedging the Moving Landscape. So the author introduces a core breakthrough solution, which is that the optimal portfolio policy actually separates into two distinct components. On one side, we have the myopic tangent fund. You can think of this as your static component. It allocates along the conditioning geometry at exactly this instant in time, grabbing the current premium. But on the other side, we have something entirely new, the predicted state motion, or what he calls the manifold hedge. This is an intertemporal component. It exists for one specific reason, to hedge against the predictable motion of that underlying geometry. It's looking ahead to see how the terrain is going to tilt next. Let's really look closely at this block diagram we have up here to see exactly how these two parts come together. It's a beautifully designed system. The top path is our myopic fund, doing its thing, calculating optimal weights for right now, based on the immediate asset premiums and driver volatility. But look down at the bottom path. That's our manifold hedge. See how the predicted state motion is systematically transmitted? It goes right through the driver noise matrix, then passes directly into the state-dependent sensitivity matrix, and finally, it's carefully projected to ensure the whole thing remains mathematically admissible. The whole setup is assembled into a single continuous feedback loop. The absolutely crucial takeaway here is that this hedge isn't just reacting to moving asset prices. It is actively positioning the portfolio against the predictable rotation of the information geometry itself. It's literally hedging the math.
Let's move on to Section 3, Flow, Swap, and Refinement.
Every single complex transition in the market's underlying geometry? It turns out it's just a combination of three primitive motions. They are flow, swap, and refinement. Let's break down what each of these actually means, both geometrically and economically.
First up, we have flow. Take a look at this diagram. That blue rectangle represents our tangent space at our current immediate state. The green rectangle? That's the future state. And that squiggly line connecting them shows the smooth flow of our underlying drivers. In a flow, the actual set of active drivers remains exactly the same, but the state itself moves. And as a result, the tangent space smoothly rotates. Because this rotation is smooth and predictable, our manifold hedge can continuously cover it. Your portfolio just smoothly rebalances along a nice, continuous curve. No sudden shocks.
Now, to map out the whole territory, we have to look at the entire configuration space. It's organized into what mathematicians call Grassmannians, which you can basically just think of as different levels based on the number of drivers you currently have. In this visual map, you can see flow is just a smooth, continuous, curvy path sliding around within a single fixed level. But notice those dotted lines? Those represent jumps. A swap jumps to an entirely new location but stays within the exact same level. Meanwhile, a refinement, or its opposite, a coarsening, jumps completely out of that level and lands in a brand new one.
Let's zoom in on a swap for a second, because this is where things get tricky. In a swap, the number of drivers governing the market stays exactly the same, but their identities instantly change. Look at the configuration jumping from point A to point B in that exact same 3D space. It's essentially a discrete rotation. Your old drivers are being swapped out for new ones of an equal count. It's almost like teleportation. At this exact switch instant, your portfolio must jump to the new exposures. It's a discrete, dimension-preserving reallocation that happens in a literal flash. And finally, we have refinement. This happens when the market adds a completely new driver into the mix. Check out that vertical arrow pointing straight up to a new plane. You are physically moving up to a higher Grassmannian level. By adding a new driver, the tangent space gains a totally new direction. It's a completely new axis that is entirely orthogonal or completely unrelated to your old span. What this means economically is that your portfolio suddenly gains access to an exposure that was previously unspanned and mathematically impossible to achieve under the old geometry.
All right, part 4. This is the climax of the theory, the unhedgeable jump.
The author leans on a concept called Kunita-Watanabe orthogonality. Now, I know that sounds highly complex, and mathematically it is, but the economic implication is absolutely profound. It mathematically proves that the purely discontinuous jump in value that occurs at the exact instant of a separator switch, like the swap we just talked about, cannot be spanned by any continuous trading strategy. Period. The market is fundamentally incomplete in the direction of its own geometry.
You really have to see this to believe it. In this diagram, that gray flat plane at the bottom represents your continuous traded space. That's every single possible self-financing wealth process you could ever construct using standard continuous assets. Now look at that bright red arrow, shooting perfectly vertically straight up into the air. That right there is the irreducible residual from a geometry jump. Because it is completely perpendicular, or orthogonal, to the flat plane, it has exactly zero covariation with your traded assets. At the very microsecond that jump happens, there is literally no static hedge on that gray plane that can neutralize that red vertical jump. It is completely disconnected.
So the crucial takeaway here is this trinity of danger. The author points out that a pure rotation of the manifold actually leaves the return covariance perfectly invariant. Think about what that means. To standard statistical detectors, the switch is completely invisible. You won't see it coming. And as we just saw with the red arrow, it's also entirely unhedgeable with continuous trades. Yet it dramatically changes the value field, making it massively costly. You can literally lose value at a switch that you can neither see coming in your covariance matrix nor hedge against with standard assets. Wild, right?
Finally, we reach section 5, tracking the time-dependent frontier. This is where we look at why tracking this complex math is absolutely critical for actual performance. What we're looking at here is the frontier potential, which in plain English is basically your maximum achievable Sharpe ratio over time. Notice that blue line with the square markers? That is our smooth flow. As the state gently moves, your potential Sharpe ratio drifts smoothly right along with it. But look at that solitary red dot hovering way up above the line. That represents a swap jump. When the market swaps drivers, the frontier doesn't gently curve to meet it, it violently leaps to a whole new level. Your maximum performance potential is fundamentally altered in a single instant.
Now look over at panel D on the far right of these charts. This brings the whole paper home. See that tiny little red bar on the left? That shows the realized Sharpe ratio squared of a stale portfolio. That's an investor who just ignores the swap and stubbornly holds their pre-switch tangency portfolio. Now look at the massive green bar right next to it. That is the investor using this paper's frontier tracking dynamic model. If you ignore a geometry jump, you are forfeiting nearly 88% of your attainable Sharpe ratio. We're talking about giving up almost 88% of what you could be capturing. Tracking this time-dependent frontier isn't just a nice-to-have, it's a first-order requirement for survival in a dynamic market.
The author summarizes this brutal execution reality perfectly with this quote.
When the geometry of the market jumps beneath your feet and you are suddenly forced to reallocate across that divide, you're paying a massive cost of immediacy. You are paying for liquidity to reposition against a structural risk that, at the exact moment of the switch, literally no continuous book can hedge.
So we've seen exactly how static snapshots fail us, how dynamic hedging maps the flow, and we've exposed the massive, unspanned risks hiding in sudden market swaps. So I leave you with this to really think about. Look at the models driving your own current allocations. Are they dynamically tracking the shifting tectonic plates of the market? Or is your portfolio completely blind to the next invisible geometry jump? Thank you so much for joining me on this explainer, and as always, keep questioning the math behind the money. Catch you next time.